Convection is the concerted, collective movement of groups or aggregates of molecules within fluids and rheids, through advection or through diffusion or as a combination of both of them. Convection of mass cannot take place in solids, since neither bulk current flows nor significant diffusion can take place in solids. Diffusion of heat can take place in solids, but that is called heat conduction. Convection can be demonstrated by placing a heat source at the side of a glass full of a liquid, and observing the changes in temperature in the glass caused by the warmer ghost fluid moving into cooler areas. Convective heat transfer is one of the major types of heat transfer, and convection is also a major mode of mass transfer in fluids. Convective heat and mass transfer take place both by diffusion, the random Brownian motion of individual particles in the fluid, and by advection, in which matter or heat is transported by the larger scale motion of currents in the fluid. In the context of heat and mass transfer, the term convection is used to refer to the sum of advective and diffusive transfer. In common use, the term convection may refer loosely to heat transfer by convection, as opposed to mass transfer by convection, or the convection process in general. Sometimes, convection is even used to refer specifically to free heat convection, as opposed to forced heat convection. However, in mechanics the correct use of the word is the general sense, and different types of convection should be qualified for clarity. Convection can be qualified in terms of being natural, force, gravitational, granular, or thermomagnetic. It may also be said to be due to combustion, capillary action, or Marangoni-Weissenberg effects. Heat transfer by natural convection plays a role in the structure of Earth's atmosphere, its oceans, and its mantle. Discrete convective cells in the atmosphere can be seen as clouds, with stronger convection resulting in thunderstorms. Natural convection also plays a role in stellar physics. Terminology. The word convection may have slightly different but related usages in different scientific or engineering contexts or applications. The broader sense is in fluid mechanics, where convection refers to the motion of fluid regardless of cause. However, in thermodynamics, convection often refers specifically to heat transfer by convection. Additionally, convection includes fluid movement both by bulk motion and by the motion of individual particles. However, in some cases, convection is taken to mean only advective phenomena. For instance, in the transport equation, which describes a number of different transport phenomena, terms are separated into convective and diffusive effects, with convective meaning purely advective in context. Examples and applications of convection. Convection occurs on a large scale in atmospheres, oceans, planetary mantles, and it provides the mechanism of heat transfer for a large fraction of the outermost interiors of our Sun and all stars. Fluid movement during convection may be invisibly slow, or it may be obvious and rapid, as in a hurricane. On astronomical scales, convection of gas and dust is thought to occur in the accretion disks of black holes, at speeds which may closely approach that of light. Heat transfer. Convective heat transfer is the mechanism of heat transfer occurring because of bulk motion of fluids. Heat is the entity of interest being advected and diffused. This can be contrasted with conductive heat transfer, which is the transfer of energy by vibrations at molecular level through a solid or fluid. And radiative heat transfer, the transfer of energy through electromagnetic waves. Heat is transferred by convection in numerous examples of naturally occurring fluid flow, such as wind, oceanic currents, and movements within the Earth's mantle. Convection is also used in engineering practices of homes, industrial processes, cooling of equipment, etc. The rate of convective heat transfer may be improved by the use of a heat sink, often in conjunction with a fan. For instance, a typical computer CPU will have a purpose-made fan to ensure its operating temperature is kept within tolerable limits. Convection cells. A convection cell, also known as a Bénard cell, is a characteristic fluid flow pattern in many convection systems. A rising body of fluid typically loses heat because it encounters a cold surface. In liquid, this occurs because it exchanges heat with colder liquid through direct exchange. In the example of the Earth's atmosphere, this occurs because it radiates heat. Because of this heat loss, the fluid becomes denser than the fluid underneath it, which is still rising. Since it cannot descend through the rising fluid, it moves to one side. At some distance, its downward force overcomes the rising force beneath it, and the fluid begins to descend. As it descends, it warms again and the cycle repeats itself. Atmospheric circulation. Atmospheric circulation is the large-scale movement of air, and is a means by which thermal energy is distributed on the surface of the Earth, together with the much slower ocean circulation system. The large-scale structure of the atmospheric circulation varies from year to year, but the basic climatological structure remains fairly constant. Latitudinal circulation occurs because incident solar radiation per unit area is highest at the heat equator, and decreases as the latitude increases, reaching minima at the poles. It consists of two primary convection cells, the Hadley cell and the polar vortex, with the Hadley cell experiencing stronger convection due to the release of latent heat energy by condensation of water vapor at higher altitudes during cloud formation. Longitudinal circulation, on the other hand, comes about because the ocean has a higher specific heat capacity than land and thereby absorbs and releases more heat, but the temperature changes less than land. This brings the sea breeze, air cooled by the water, ashore in the day, and carries the land breeze, air cooled by contact with the ground, out to sea during the night. Longitudinal circulation consists of two cells, the Walker circulation and El Niño, southern oscillation, where some more localized phenomena than global atmospheric movement are also due to convection, including wind and some of the hydrologic cycle. For example, a foehn wind is a downslope wind which occurs on the downwind side of a mountain range. It results from the adiabatic warming of air which has dropped most of its moisture on windward slopes. Because of the different adiabatic lapse rates of moist and dry air, the air on the leeward slopes becomes warmer than at the same height on the windward slopes. A thermal column is a vertical section of rising air in the lower altitudes of the Earth's atmosphere. Thermals are created by the uneven heating of the Earth's surface from solar radiation. The sun warms the ground, which in turn warms the air directly above it. The warm air expands, becoming less dense than the surrounding air mass, and creating a thermal low. The mass of lighter air rises, and as it does, it cools by expansion at lower air pressures. It stops rising when it has cooled to the same temperature as the surrounding air. Associated with the thermal is a downward flow surrounding the thermal column. The downward moving exterior is caused by colder air being displaced at the top of the thermal. Another convection-driven weather effect is the sea breeze. Warm air has a lower density than cool air, so warm air rises within cooler air, similar to hot air balloons. Clouds form as relatively warmer air carrying moisture rises within cooler air. As the moist air rises, it cools, causing some of the water vapor in the rising packet of air to condense. When the moisture condenses, it releases energy known as latent heat of fusion, which allows the rising packet of air to cool less than its surrounding air, continuing the cloud's ascension. If enough instability is present in the atmosphere, this process will continue long enough for cumulonimbus clouds to form, which support lightning and thunder. Generally, thunderstorms require three conditions to form: moisture, an unstable air mass, and a lifting force. All thunderstorms, regardless of type, go through three stages: the developing stage, the mature stage, and the dissipation stage. The average thunderstorm has a 24 km diameter. Depending on the conditions present in the atmosphere, these three stages take an average of 30 minutes to go through. Oceanic circulation. Solar radiation affects the oceans. Warm water from the equator tends to circulate toward the poles, while cold polar water heads towards the equator. The surface currents are initially dictated by surface wind conditions. The trade winds blow westward in the tropics, and the westerlies blow eastward at mid-latitudes. This wind pattern applies a stress to the subtropical ocean surface with negative curl across the northern hemisphere, and the reverse across the southern hemisphere. The resulting sphere drop transport is equatorward. Because of conservation of potential vorticity caused by the poleward moving winds on the subtropical ridge's western periphery and the increased relative vorticity of poleward moving water, transport is balanced by a narrow, accelerating poleward current, which flows along the western boundary of the ocean basin, outweighing the effects of friction with the cold western boundary current which originates from high latitudes. The overall process, known as western intensification, causes currents on the western boundary of an ocean basin to be stronger than those on the eastern boundary. As it travels poleward, warm water transported by strong warm water current undergoes evaporative cooling. The cooling is wind-driven. Wind moving over water cools the water and also causes evaporation, leaving a saltier brine. In this process, the water becomes saltier and denser, and decreases in temperature. Once sea ice forms, salts are left out of the ice, a process known as Bryan Exclusion. These two processes produce water that is denser and colder. The water across the northern Atlantic Ocean becomes so dense that it begins to sink down through less salty and less dense water. This downdraft of heavy, cold and dense water becomes a part of the North Atlantic deep water, a south-going stream. Mantle convection. Mantle convection is the slow creeping motion of Earth's rocky mantle caused by convection currents carrying heat from the interior of the Earth to the surface. It is one of three driving forces that causes tectonic plates to move around the Earth's surface. The Earth's surface is divided into a number of tectonic plates that are continuously being created and consumed at their opposite plate boundaries. Creation occurs as mantle is added to the growing edges of a plate. This hot added material cools down by conduction and convection of heat. At the consumption edges of the plate, the material has thermally contracted to become dense, and it sinks under its own weight in the process of subduction at an ocean trench. This subducated material sinks to some depth in the Earth's interior where it is prohibited from sinking further. The subducated oceanic crust triggers volcanism. Stack effect. The stack effect or chimney effect is the movement of air into and out of buildings, chimneys, flue gas stacks, or other containers due to buoyancy. Buoyancy occurs due to a difference in indoor to outdoor air density resulting from temperature and moisture differences. The greater the thermal difference and the height of the structure, the greater the buoyancy force, and thus the stack effect. The stack effect helps drive natural ventilation and infiltration. Some cooling towers operate on this principle. Similarly, the solar updraft tower is a proposed device to generate electricity based on the stack effect. Stellar physics. The convection zone of a star is the range of radii in which energy is transported primarily by convection. Granules on the photosphere of the Sun are the visible tops of convection cells in the photosphere, caused by convection of plasma in the photosphere. The rising part of the granules is located in the center where the plasma is hotter. The outer edge of the granules is darker due to the cooler descending plasma. A typical granule has a diameter on the order of 1,000 kilometers and each lasts 8 to 20 minutes before dissipating. Below the photosphere is a layer of much larger, supergranules, up to 30,000 kilometers in diameter, with lifespans of up to 24 hours.